Well, it's 11, but not many people are here yet.
This is a small cohort.
Well, I'll get started anyway. So we're getting our new security system installed today, and the main panel for that is in my downstairs office. So I'm not going to be down in my downstairs office right now. But that's why I don't have a green screen. But you may also hear some drilling. Let's see. So there's a final project, hopefully you know about. I was going to have that due the last week of classes, but I think we might actually be able to have it due after the last week. So like during exam period. I was hoping to get some feedback on that, because on one hand, it's really nice to just have it done. On the other hand, oh, and it's nice for me because then I could have longer to grade. But on the other hand, if you had the flexibility and could spend an extra week on it, then some people might benefit from that. So I was wondering if people had any opinions one way or the other.
I think more time to collect data would definitely be useful.
Yeah, I agree. If there's like room for, like in terms of extending the final paper, like for me, the draft paper doesn't even necessarily need to be like pushed back if what's expected from like data analysis and discussions isn't as like, if it's not the same expectations for the final paper.
Okay. Anyone strongly opposed to an extension on the final submission? I guess if you were, you're still completely allowed to hand it in at the normal time. Okay, so I will update the schedule on that. I know a bunch of you have started collecting data, so that's good. If you haven't yet, please make sure to check out the Discord channel that's asking for participants, and please do participate. I need to do that myself. It was on my calendar and I haven't done yet, but I'm going to try to participate in everyone's study because that just seems like it'll be good for me, and it'll be easier for me to then understand and grade your project later. Let's see. So then the final write-up is going to be due probably a week after classes end. But the last week of classes, I still want to have in-class presentations. So you'll have to present whatever you've got finished at that point. So if there's not some final analysis that has been done, if you don't have all your results collected, just do the best you can with what you have. Similarly, with the draft that's due on Saturday, I'm going to grade it like I would just a normal final submission. So if you have no results, I'll put a big results question mark with the expectation then that your final draft will just correct all of that. So the more you have in the rough draft, the better, the more feedback I can give you. Similarly, I want to figure out a way to give peer feedback. So what I was planning on doing is asking everyone to read over at least 2 other submissions and give their feedback. I thought what I might do is ask people, please choose one report that you want, of all these titles, please choose one you want to read, most want to read. And then I will assign a second one to make sure we get broad coverage. But if you have other ideas on how to try to balance what people are most excited about with making sure people do get peer feedback, please let me know. And the last thing I wanted to mention, so thanks again for volunteering to give these presentations. So just like the write-up, I haven't really given you any details on the specific format. It doesn't really matter. If you want to use Word or you want to use LaTeX, if you want to make it look like a conference paper or journal article, all of that's fine. And just like for the reading paper presentations today, I haven't really given you any guidelines. I basically said, well, let's plan to spend about 20 minutes on something you think the class will find. It's something that's relevant to your project, so it shouldn't take you a whole lot of extra work. And then the class will benefit from learning about this new thing. So what I'd like to do, I've set up a new channel in Discord, which is called Paper Presentation Q&A. So after each of these, 20-minute or so presentations, what I'll ask you to do is for each group, say one thing you liked about the presentation or the work, and one thing that you think either the presentation or the work could be improved on. So that's just a really low stress way of letting you give some feedback, because we can all of us have things that we can do to improve our presentation ability. I strongly believe that's an important thing to be able to do well. So by giving feedback to each other, then you'll get another chance to get feedback. So with that, I think I'll hand it off to Tobias and Graham, who have volunteered to go first.
All right, I'll just get my screen set up. And if you guys could let me know, you can see the presentation.
Yes.
Beautiful. Okay, so I'm not going to waste a bunch of time. We are going to show you this paper called Learning to Summarize from Human Feedback. And it's a very new paper. It's in ICLR 2020. So their objective is to summarize a text so that humans think that the summary is a high quality one. And in terms of a summary, they're looking for text that is fewer than 48 tokens long. And so I think we all understand what the idea of a summary is. That's just to provide the original content, the main points of it in a shorter form. So one of the original questions we had was why 48 tokens? It seemed fairly arbitrary. And I guess in truth,
Tobias, just to, okay.
Yeah, so you go ahead, Graham.
It what didn't go to the next slide. I thought.
Oh, it didn't?
It wasn't presenting.
Is it on the next slide now?
Now it is.
That is very weird.
Yeah.
It was delayed then? Okay.
I think so.
When I change this one, I guess we'll wait and see if it changes. Goody. So the 48 tokens is intended to just be a balance between not too many words and not too few. So what tends to happen is that the more words you put, the more people like the summary, the more they rate it as representative of the topic. And that makes sense if you think about it. But the goal of a summary is to use as few words as possible. So this 48, they kind of figured was a balance between giving enough information, but not too much. It also allows there to be enough of an overlap between their generated summaries and the reference summaries. So a reference summary here is what they're comparing against. Okay, so can we see this next slide now?
Sorry, quick question. This is an RL method. This is not a supervised learning method.
It's a mutant.
Oh, okay.
Yeah, you'll see it. It's a big wad of stuff that's all jammed together.
Very attractive description.
Yeah. So can we see the challenges slide now?
Yes, that the transition was fine.
Beautiful. So the challenges in doing this kind of thing are, first off, we have to identify the important text. And text, if you guys are not familiar with working with it, we as humans think that text is very structured and follows a nice set of rules, but in reality, it does not at all. Text is really unstructured, and it's hard for computers to extract meaning or determine what text is important and what isn't. So in response to that, and we have this difficulty of how to measure what good text is and what makes a good summary. And we also have conflicts about the reproducibility of evaluations. So we kind of have one method that has a good reproducibility and another method that has a better correlation to what we actually want. So I'll go over those more in detail later. But we'll talk about the training data first. So for this, they used the Reddit TLDR data set. And if anybody is familiar, everybody should be mostly familiar with Reddit, but it's just basically a bunch of communities organized in a forum, sort of quasi-social media. And this data set is built up from summaries written by Redditors that are basically TLDR, too long didn't read. So some subreddits have a requirement that you have to include a TLDR, which basically, if you're going to write too much, lots of people won't read it. So you have to put this little summary for those people. So it ends up being this big resource of approximately 3 million human written summaries of larger content. So I thought, when I originally saw this idea, I thought this was actually a pretty clever way to get human written summaries and in turn the backing stories for it. The authors of this work filter it down to 123,000 different TLDRs. And they use topic and content filtering to take out things that are obscure or abstract, length filtering to look at ones that are too long, too short, both on the article and the summary, and duplicate filtering, that they remove all of the duplicates from the set. So they reduce this 3 million down to 123,000. The main claims of their work is the primary thing is that there's a discrepancy between what's usually being optimized in summary generation and the objective. So what they mean by this is that we make the general assumption that any human written summary is a good summary, and we try and optimize the machine learning models to produce human written summaries. What these guys have done is, instead of doing that, they've tried to make it optimize for measurements of human feedback. How good is the summary, rather than was it close to a human summary? They claim that these human generated models generalize better. So across different topics, different domains, they actually do a better job of summarizing. And in the same terms as the first point, they argue that maximizing the log probability of word occurrences is not the best way to train language models. So this is generally the way that we do train language. So I'll go over that in more detail in a coming slide. And this figure here is their primary takeaway from their work. And basically, you see at the top, they have their orange line, that's the human feedback models, and the general supervised learning models are green, and the pre-trained only is blue. So this is basically a transformer type generative model, and the pre-trained is basically just using off-the-shelf GPT-3. GPT-3 like, I should say, it's not actually GPT-3. The green one is supervised, so that's basically a fine-tuned GPT-3. The reference summaries, so here, I think what the point they're trying to make is that at 50%, person is half as likely to choose reference summaries, and the human feedback model is actually more likely to be selected over the summaries that the humans wrote. So what they're trying to claim is that their model produces better summaries than humans do, which is a pretty outstanding claim. So,
sorry,
yeah.
Tobias, quick question about the previous slide.
Okay.
So the y-axis fraction preferred, so every single one of these produced summaries are compared to a human reference baseline of some sort, and that's the proportion in which people prefer the human feedback one over the reference summary. Is that, am I understanding that right?
It sounds like it, yeah. So basically, the humans are given two summaries, and they have to judge which one they like better. So what they're saying is that with their human feedback model, people pick the generated summary 0.6 to 0.7. So 60 to 70% of the time. So that implies that they only pick the reference 30 to 40% of the time. Okay, so maximizing log likelihood. So the typical way that we train generative models is to maximize the log likelihood of the next word. You basically feed the model a bunch of tokens and you ask it, hey, what comes next? And you just keep repeating that, and you feed it what it said before to keep it generating the next word and the next word and the next word. So what this does is just produce the most likely series of tokens. And we have some kind of clever ways of working around the fact that it shouldn't be deterministic. It should be somewhat random. So we have a temperature parameter that generally controls how far off the most common token you'll get. So we have kind of clever ways of making this feel human. But really, the biggest problem with this is that what it's going to say is not necessarily true at all. The model doesn't learn facts, it only learns to generalize things. So if you ask it, you prime it with the words "my birthday is on" and ask it to predict what's next, it's almost certainly not going to give you the right answer. It's going to give you the most common birthday. My birthday is on Monday, my birthday is on Tuesday, this kind of thing. It's not going to answer the question. It doesn't know facts. So when humans read summaries, we're looking for things that are true about the text. So you can't say the birthday was on the most common long likelihood word, because that's going to be wrong. The way we typically measure summaries, so this is a tricky thing, right? We have some idea of what a good summary is and what a bad summary is, and we need some kind of concrete way to evaluate it that's reproducible. So in general, we still use this ROUGE metric as our most common evaluation. And what ROUGE is a way of comparing a candidate summary with a reference summary. So the candidate is what's generated by the model, and the reference is whatever you're training on. So all ROUGE is, and it's really simple, and I think intuitively everybody agrees that ROUGE is not great. It's just we don't have anything better. It measures the amount of word overlap between a candidate and a reference. So when they talk about recall in ROUGE, they're talking about the total number of shared words. So however many words the reference and the candidate have in common, and the number of reference words. And for precision, instead of the reference words, it's the number of candidate words. So basically, we're trying to say how frequently these different words overlap. And the biggest, most obvious problem with ROUGE is that this doesn't account for synonyms. If you use a different word that means the same thing, it's going to decrease your ROUGE, but not decrease the quality of your summary. So there's a question, yes, with ROUGE, can you never outperform the reference summaries? I think that would be true, yes. If you optimize for ROUGE, I don't see a way that you could outperform the reference summaries. Because at best, it would match them, which is boring. Good point. So just to give you a concrete example of ROUGE, I just have a proposed summary and a reference. So here, the summary would be what was generated by the model, and the reference would be the Reddit TLDR. So here you can see most of the words match up. Most of the words in the summary are present in the reference. So this gives us a poor recall, but a reasonable precision. Okay, and the reason why it doesn't have a perfect precision is because small is a synonym of little. And I'm sure we're going to be sharing these slides, I assume. So if you guys want to go through this in detail for whatever reason, you can go ahead. But you get the idea that this is an excellent summary of this text. It's shorter, it's better, but still the ROUGE recall is poor. So these exist. Yep.
Once you're done, if you can drop your slides and ideally the original paper or a link to the original paper into Discord. That way we can have a record of it and everyone can easily access it in the future.
Sure, yeah. These existing automatic metrics for evaluating summary quality have received criticism for poor correlation with human judgments, and you can see that. Right? So when we look, sorry, that's a little bit blurry. This graph is in the paper, and what they're trying to say is that their models, all of the summary of blue lines are their different reward models at different phases, have a higher fraction that are preferred to the reference. And across the bottom here, what they're doing is they're saying the best summary selected from generated summaries using each of the methods. So they use one of their generative models to produce, say, 2048 summaries, and then they pick the best one according to each metric and ask the humans to compare it to the reference. And with ROUGE, we peak quite early. We stop getting better summaries no matter how many we produce. People just don't like the ROUGE model. And given the way that is, the way that ROUGE works, I don't think we should be surprised by this.
Sorry, Tobias, did you mention what RM is? You said reward model. Did you already mention it and I just missed it? Or?
No, so we haven't gone through it in detail. We're just trying to bash ROUGE right now.
Oh, okay.
and then we're going to move on to showing you in the next couple slides. Graham's going to tell you guys all how everything works, and hopefully it'll all tie together.
Perfect. Thank you.
Is this already the RL type model? Like the reason that these are increasing with increasing number of N is that the reinforcement learning is causing the models to get better?
That is, yeah. So the reward model is the reinforcement model, and yes, kind of.
Okay.
It's more that I'd say it's more that they're actually optimizing for human feedback, whereas ROUGE is looking for words to specifically match between the references and the candidates. This is optimizing for quality. It's optimizing for what you actually want.
Yeah. I was almost going to say that like it's like apples and oranges because ROUGE doesn't use RL at all, right?
No, ROUGE is just straight up simple. Does the word match or not? Even if you put a plural on it, ROUGE won't work.
Okay, so then that's noise, seeing that it changes with N.
No. So in general, like the models start out producing a very poor quality, right? So like at 1, they're only preferring, no matter which model, when you only generate one sample, the humans are preferring that one sample, the reference to that one sample most of the time. If that makes sense. So the metric that they use to weight that sample is what is controlling how these go up. And the reward model is what it's using to predict whether or not the people are going to like it. And they're basically trying to say that people do like it better. And if you just use ROUGE, the people never learn to like it better. And at some point, the models start to fit better to ROUGE, but it doesn't match the actual quality.
Okay, thanks.
Yeah.
I think a clarifying point here is that none of these things are actually like model specific. It's only the metric specific. So when we're talking about the reward model 4 or 3 or ROUGE, this is not using their RL model. This is just saying using some other generating model, we're going to generate a whole bunch of different samples, pick the best one as says one of these metrics, and then see if people actually like that. So this is entirely a Bash ROUGE slide where they're saying that even when you have 2,000, like you would have the same 2,000 options for ROUGE as well as the reward model 4, and the ones that ROUGE likes the best, the people don't like the best. But the ones that the reward models that they made, people tend to like more.
Just sorry, before you go on, just commenting because I think this is the only time. Like, why only ROUGE? Because there's other metrics you could use. Because like when you were describing ROUGE, it sounds like to me the blue score they're using machine translation, and so I don't know. I feel like this is an incomplete analysis because there's other metrics, and they all have their own foibles or whatever. But I don't think this gives an entirely perfect picture. But anyways, I'll just leave it at that. But.
No, that's okay. I mean, Blur isn't better than ROUGE. It has the exact same problems. It just has certain punishments that apply. It's basically the same thing. And in the paper, like we didn't talk about it. They do use n-gram models and stuff for but we just felt it wasn't important. The idea of matching any kind of token exactly is flawed. And it exists in all of the different automatic metrics we have for these kind of comparisons just because of the way they are. The good thing about them, like you can bash them all you want, but they are repeatable. You can optimize for ROUGE and Bleu, but you can't optimize for humans necessarily because if you get a different batch of humans, they're going to say different things. And this is optimized to their batch of humans. So if you repeat this study, you're going to get all of the flaws that come with doing that.
Okay, I'm going to take over. Tobias is going to stay on this. I'm going through Zoom browser, and I keep on getting disconnected. So it might happen, but I'll jump back on. So their method, kind of the overarching process that they had in this was to get human feedback into this loop. So in big batches, they sent out a whole bunch of said, which one do you like better? Kind of the eye doctor. Do you like 1 or 2? And then from all of this data that they collected, they made a supervised network to predict what ones humans would prefer. And so they call that the reward model. And then using PPO in their reinforcement learning part, they optimize with that reward model. And the next slide's got a nice little picture of what that all looks like. So the first step is the collecting the human feedback, and they send out a huge amount of these to everybody. I think the paper doesn't say exactly, but they've got, I don't know, more than 20 labelers doing this for quite some time. And then they look at 2 individual summaries and they just choose which one they like better. And from this, get a loss and go forward with that as the reward model. So it is maybe one thing to mention that even though they're big on saying that we were perhaps optimizing the wrong thing before, they are now optimizing on a neural network. So you're kind of slowly getting away from the thing that they're trying to optimize anyway. Okay, next slide.
Sorry,
They
Graham,
have a whole bunch of model. Yeah.
Oh, sorry. I had a quick question about your previous slide. So in step 2,
Sure.
when you calculate when you learn the reward model for each summary, so is RJ just 1 and RK just 0 if J is better than K?
Is RJ 1 if R?
I don't think so. No, it shouldn't be 0. It'll be somewhere
I think so.
between 1 and 0.
Okay.
It's RJ.
I'm just wondering how you use the human label in order to update the reward model.
So the reward model is just going to predict whether or
Well,
not
just
the
didn't-
human's going to like it better. So the output's going to be a probability on each side.
Okay.
I get from your response that doesn't make a whole ton of sense.
No, sorry. I'm just processing that in my head. Yeah, I guess that
Okay.
does kind of make a bit more sense. Okay, cool.
Okay.
And then after all the training is done, are they
Just like a class.
after all the training's done, are they evaluating on the trained reward model, or are they going to go back and evaluate on people?
They eventually go back and evaluate on people, but they use the reward model to do the RL training. I feel like I've got some lag right now. I've got strange.
You are laggy, but that's fine. You can just keep going.
We may have lost him.
Or you can quit. That's cool too. Tobias, are you able to take over?
Yeah, sure. Yeah, I'll just babble until Graham comes back, then he can interrupt me. The models that they use are all transformer based, or all intended to be transformer based, and they're similar to GPT-3 but slightly smaller, although the thing to keep in mind is that these are still huge models, 1.3 and 6.7 billion parameters. At some point in the paper they mentioned 300 to 400 GPU days worth of training is put into this thing, so it is not a small model. Pre-trained models are padded with high quality.
I'm back.
Oh, okay. Go ahead, Graham.
Yeah, sorry about that. This is very frustrating. So yeah, we were thinking it kind of seems like cheating a little bit, but the pre-trained models are padded with high quality summaries of other good reference summaries that are from the data set. So kind of another one. So they call that the primate is just choosing which of the two summaries that the human will like better. As we said before, supervised training, it's also a transformer. Everything's a transformer in this paper. And because it is itself trained, there could be some problems. And we have a graph later to illustrate. But what they were trying for in this is to train a reward of good quality rather than just a human created as the right answer. And humans are going to have a range of how good they are or what they are maximizing, because you might want completeness or you might want brevity. And so those two things are opposite forces. Okay, so next slide, we show the what's happening in the human feedback situation. We have each byte pair encoding token as a time step, and then it predicts each one and eventually gets to its final output. And then we're able to kind of in the future pick better steps to make along the way. And so in the reward model, or in the reward function, we see that it starts off with the reward model that we trained, the supervised training, and then we are subtracting off how much we are different than that initial policy. So this is just a KL divergence term with a coefficient in front of it. And so the idea is that we're able to explore a bit, but because we started with fine tuning and that padding, we don't really want to explore too far away because we start at such a good baseline. So this graph is why that KL divergence term needs to be here. If we leave it only to the reward model prediction, it will ask the network to go way off into no man's land, very far away from that where we started. And we can see that this bottom line, the solid line, is their actual preference. So it starts to get better as we go a little far away, and then it plummets later on. Okay, so next slide is quality improvement. They looked at all. Go ahead.
Oh, I just had a question about the x-axis. So that was the magnitude of the KL divergence, not like changing beta.
So x-axis is changing beta. I think that's fine. Yeah. Farther away than, or sure, magnitude of KL divergence. As they let it get farther away, it gets worse. So they want to keep it fairly close. For the quality improvement, they judge things on 4 different scales. So coverage, which was how much of the point of the main article, anything that was untrue or not said. Coherence is just, did it make sense? Was it English? And just an overall look. So then on the next slide, we have a graph that shows that human feedback in yellow is better all the time, but perhaps not wildly better. So especially in things like coherence and accuracy, it is very close to some runners up. And oddly enough, reference summary and accuracy actually does the worst. So a little bit confused by that. One of they took this thing that they have trained on the TLDR data set, and they switched it over to the CNN-DM, which is a bunch of news articles, and they found that it does quite well. It doesn't do as well as the CNN-DM supervised network, but their large model comes very close. And we have a graph on the next page to show. And they also wanted to point out that their references or their summaries were often quite a bit shorter, and we have a summary log length to average quality graph to show that in general what they've seen is length is always humans see as a benefit. And so because theirs was shorter, this is their way of saying ours longer, we might have actually been the same or better. Whether that's true or not, I'm not sure.
So that
But
is
that-
the end of our talk. Sorry for it being a little bit over.
That's okay. Thank you. So is the take-home message, if you want to do summarization, you should use this technique? Or do you think that there are better things out there and this needs more work?
So it really depends on your resources. Like, this thing is cool. It seems to work really well. I love all of the ideas, but really it's going to be slow. This thing is running 3 separate transformers and RL. It's not, I mean, it's not for a mobile phones. But
Okay, so they don't really do a performance versus wall clock time.
Yeah.
Okay.
But I mean, at the end of the day,
Implicitly, I really like the idea.
Go ahead, Grant.
Okay, so I think we should probably move on.
I a fairly strong point that they made.
We should probably move on to the next one to make sure we get everyone in. Who wanted to present next? And please remember to drop some comments in the chat for Tobias and Graham.
I'll go next.
Great.
Okay. So I'm gonna try and have the Discord open on my other screen because my Wi-Fi also tends to cut in and out. So maybe if it does, if someone could just let me know in that, I'll try and have that open the whole time. Well, and because some stuff will work and then the connection will pause with Zoom. But okay, can people see my screen?
Yep, you're good.
Okay, so today I'm presenting the paper Why, What, and How to Log by Jack Mostow and Joseph E. Beck. It's kind of an older paper, it's from 2009, and it was published to EDM, that's the Educational Data Mining Conference. As I've kind of mentioned here and there, my project as well as my like the area that I work in is educational technology. So this is going to be, and this is from the Educational Data Mining Conference. So this is going to be largely focused around educational data mining and tutor systems. But I think that it's still really useful and important for this kind of class because I think being able to like really explain the limits and like the ideas behind what you're logging when you're doing human participant studies is super important. So hopefully some people find this useful. So this is based on their Listen project. So I'll just quickly explain which that is, which is Listen was a reading tutor which used speech recognition to listen to children read aloud and then help them read aloud. So they based these guidelines for data logging based on the 15 years that they have of logging, exploring, and analyzing the millions of events from this Listen project. So as the title suggests, this will be broken down into why, what, and how. So the why has 4 parts. So the first part is tutoring. So when you're making a tutoring system, having data that's logged that's relevant to the tutor, like be able to help the tutoring system tutor the user is pretty important. So this feeds the user model, so modeling what the user knows, as well as feeding any adaptive algorithms that you have. So one thing that's also valuable about data logging within an educational setting is reporting. So what this could mean is a report for teachers that summarizes the students' usage and progress. It could also be useful for a report for students themselves. This is for learning to read, so it wasn't really a focus in this paper, but for like adult learners or just kind of older in age, being able to know like your progress on certain things or your usage could be useful in making your own decisions for what you should focus more on. Report can also be useful for like the technical support staff to flag possible technical problems. The next part is browsing. So this is more useful in a research sense. So being able to have the log data available to understand specific characteristics and display them in human understandable form can help them explore in dynamically variable detail as well as annotate them. And then as well, overall, just mining. The more data you log, the more you're able to have educational data to mine to improve your system and potentially others. So that's the why. The what is now the meat of source of what should you log. And so this is what they found. So the first one is environmental data. So what environmental data means is what's happening like outside of the system. So since this was used in a classroom setting, it would be like the physical and social context. So is there noise going on? Did they have help from the teacher? Did they collaborate with other students? That kind of a thing. So the paper suggested computer vision, but that's kind of tricky. It's a big thing to add into a system just to kind of capture that. So there's also the potential for manually inputted data about physical and social context. It's not as reliable of a source, but it's definitely a lot easier. The next is raw input. So this one's pretty straightforward. Raw input from keyboard, mouse, and microphone interactions. Then there's interpreted input. So within an educational sense, it would be input observations that go through layers of interpretation. So what this could mean is you have the input, was the action that the user took, was it a right answer or was it incorrect? This could also be comparing the action taken to the expert decision. So like there are a lot of fields where there's not necessarily like one right answer, but like the steps that you took to get there, was that the steps that an expert would take? So then there's also the logging the student model. So this would be trying to model the estimates of the individual skills. So in a very like simple high level way, it could just be what have they been getting right and wrong and trying to assume what they know based on that. Then there's also tutor decisions. In this case, decisions that the reading tutor made. So to wait, to prompt the student, to give praise, help, all that kind of thing. And then there's tutor actions, which is the more like direct, like simplified thing, which is the direct like technical actions that the tutor took. So audio output, graphical display, that kind of a thing. Then there's also events. So this is just logging things like sessions, logins, whether it crashed, that kind of thing. And then there as well as logging observing the tutor. So this would be reconstructing the exact appearance of the screen. The paper admitted that this is a little problematic for like a number of reasons. So you could, like if you log the raw data input and the events and that kind of a thing, in theory, you could like recreate sessions, but because of like, you would need a lot more of like really fine-grained data points, as well as there's like variations in operating systems, so it could visually look different. So they suggested that like need be, you could film it probably through like screen recording, but that's going to be most useful if there's kind of, probably I'm assuming for things like research rather than actual daily use that you would log that kind of data, because that would be a lot. So the next section was how. This section is pretty straightforward. Log directly to a database, log end time as well as start time as a session, using a separate table for each type of tutorial event. And then the rest of the guidelines for this, we were pretty specific to the project of being something that exists like in a school, like on where you're not like necessarily online, you're on like the physical computer itself. So using like standard fields being student ID and computer, like they're generalizable to projects around like IP if you needed to log IP, or like participant ID. But so these ones I included just to be complete, but they are far more specific, even more to like overly specific for my project, which is education based. So then another thing was logging the non-occurrence of an event, which I thought was interesting. It's still, this type of thing is still an active topic of discussion, but it's basically logging or recording something that could have happened but didn't. So in the reading tutor's case, it would be when a word was skipped or not read. So how this relates to my project is this kind of stuff is completely foundational to my field, as well as my project for this class is, as well as the greater research project that it belongs to. So as a refresher, for those who didn't know, what I am doing in my project is modeling user data to make gameplay and learning personalized and adaptive. So the gameplay being playing this little arcade style game where users get given a sound on repeat, and then they have to shoot the item that matches that sound. Like I said, logging is the backbone of this project. The data builds the user model as well as decides the item the user sees next. The logging of the non-occurrence got me thinking where in my project, I actually do log non-occurrence of events. So when in this case, say the answer was like E, but they shot C or something, every time something got shot, it would log what was shot and its position, but as well as the position of all other items on screen, even though they weren't shot, because since it's a game for learning. So being able to play the game well is kind of like part of, or sorry, I should say that the goal of this is to make someone learn. So it's less important about like, we care less about modeling whether they're good at the game. So if they accidentally shot C when they knew the answer was E, but it was just too close, logging this type of non-occurrence of shooting the right one could help identify this type of accident from the user. So that's what I just said. So one thing that wasn't in this paper that I wanted to address, because I think it's pretty, like, I think it made sense that it wasn't a part of the paper just because it was so specific to the project that they were talking about. But that's privacy and consent. So my project focuses on Indigenous language revitalization. So the target user base is Indigenous people in Canada. So Indigenous people in Canada have historically and currently been monitored by the federal government as well as like the church and stuff. And on top of that, I'm working in language, and language data from Indigenous communities have also historically been like taken by non-Indigenous academics and used without their consent or being being given proper credit. So I think overall it's worth, no matter what project you're doing, if humans are involved in what you're logging, it's important to consider whether like it is a potential like privacy breach, whether like what the risks are around that, whether it's reasonable that you should be asking for consent about something. So so it's more important in my project, but I think it's worth at the very least, like considering and addressing, even if the answer is no, it's not that important in your own project. But so for me, I ask if it's necessary and what the potential implications of logging the data is, whether I need to disclose it or if it's reasonable to assume it's a given. So like for the greater project that this is a part of, when you log up or when you sign up, use an email, and it's probably reasonable to assume that the person knows you have their email now. But for other things, like most laymen probably don't know off the top that that's like most things are being logged. And then on top of that, how do I disclose or explain what's being logged if it's not reasonable to assume so that the user can then give informed consent? And that's my presentation.
Awesome, thank you. I really like the privacy and consent thing. I was just reading this morning how there's a popular Muslim prayer app that collects data without telling users that the U.S. military has been buying. And when you brought up, oh, they could be collecting video data, that immediately made me think of the proctoring services that some universities are using that are completely invasive, and students have to use them in some cases.
Yeah, I think there was also something in, I don't think it was Edmonton, it was in Alberta though, where some mall was outed as using like they were filming you if you looked at the directory, and then they would advertise based on like facial recognition, which I thought it was kind of funny that was a scandal, because I thought I thought this is what all malls were doing all the time. Like there's always a suspicious camera in the directory, so why else would it be there?
So the other thing I wanted to ask is, it seemed like this was kind of here are things you're thinking about when you design a project, right? Because it seems like most of the time, at least it seems like it's only when you start doing the data analysis where you're like, oh shoot, I really wish I had logged this thing. And it's kind of at that point you realize what you needed to do. Is that correct?
Yeah, I definitely would say it's very foundational. Like it's something that you would consider when building the database, for example, for your project. I'm working on web, so the database has to be there. So it's a big part of the initial modeling. And then because I work under Carrie, her thing is like everything from this paper, but it's just kind of like, it might not be useful now, but it might be useful later. So that part that I mentioned with trying to identify whether an accident was made, we're not doing that yet, but we could. We have it.
Nice. Cool. Any other comments or questions?
I'm wondering if you have any existing involvement from Indigenous stakeholders for your project.
Yeah, so with respect to my project, so the general project is something that we're calling Cree Tutor. Cree is the Indigenous language from this area, so it's the one that we're working on. And so this is pretty nascent, and there's a couple of ways that we've been trying to include Indigenous stakeholders. So for the kind of behind the scenes in terms of like the language data that we're getting, we're working with the Faculty of Native Studies and their Cree program, because they have lab language recordings. So that's like the basis for this specific project. We're also working with different communities to collect language data, and around that, the stuff around that is we're trying to build partnerships there, because there is like benefit in terms of there can be this type of like mutual partnerships in this way, where you collect language data and you help with digitization, because that's like a really big issue. And then on top of that, another part of my research is what's called participatory design. So this is where I've only been able to do one study so far, because student, and I did it in my undergrad, but where I conducted focus groups with self-identified Indigenous people. It was very small. I'm hoping to expand on it, but basically we're not currently working with any like specific community. It's much broader, and it's a lot more
of like within the Faculty of Native Studies, because like we're hoping for this to eventually be used for the Cree class there. But the initial steps are kind of like laying that groundwork and yeah, trying to rely on the participatory design, making no assumptions of what anyone wants.
Cool, thanks.
All right, thanks again, Delaney. Very cool. I think we should probably move on to Michael and Laura. So they still have 25 minutes left. So hopefully that gives them enough time.
That should be good.
Awesome.
Okay. I will start sharing my screen.
We can see it.
You can see it? Okay, good. I usually have issues with this part when I'm starting to present, so I'm glad that it is working. Okay. So we are going to be talking about the paper Probabilistic Human Intent Recognition for shared autonomy and assistive robotics. So both Michael and I work in the robotics lab under Martin Jagerson. So this kind of ties into our research. First, oh God. This is the issues I was talking about. Sorry. Okay. First, just we're going to give a kind of a general overview on assistive robotics. So in assistive robotics, we're interested in helping individuals that are living with disabilities to carry out their activities of daily living. So in most cases, they'll have like a caregiver come in and help them perform certain tasks. But if you have, say, an assistive robotic arm that you can attach to your wheelchair, then we can tie that in with whatever control interface they're already using. And they can operate that themselves in order to, say, go and pick something up off the floor that you've dropped or get yourself a glass of water, kind of returning a little bit of independence. So shared autonomy within this domain kind of works to augment the human control signals that we're mapping from, say, joystick or touch screen or whichever they're using in order to aid the human in the operation of the assistive robot. So in order for the robot to meaningfully be able to assist the human collaborator or the end user, the robot needs to be able to correctly infer what the intended goal of that user is in the first place. And this could be from a set of potential kind of task relevant goals. So this is called the task inference problem, where you're trying to learn what the intended task is. So in this paper, they kind of set out to answer this more of a high level question. It's similar to previous works on the empathic framework and tamer that we were talking about previously in class, where can the robotics autonomy implicitly observe and leverage these nonverbal human actions in order to perform human intent recognition? And I thought this figure was pretty funny. Okay. So shared autonomy in assistive robotics. So the focus is on human commands provided through a shared control assistive robotic system through the control interface. So we want to model the user's interaction with the control interface as a probabilistic goal-directed actions. And this will allow for uncertainty in reasoning about the user's intentions. So we're going to first assume that the human inputs are representative of the action that the user actually wants to take. They do this by using a recursive Bayesian filtering framework, which Michael's going to talk on in a couple slides. And they worked in the ability to kind of adjust the rationality for user personalization in order to account for like suboptimal trajectories in the human's input. So in this figure, this is kind of a high level overview of the full system. So we have, can you see my cursor? Okay, cool. The human user over here with their control inputs. So the control inputs are being sent both to the intent recognition system and the shared autonomy. Also, the assistive arm is sending its state space. So the individual angles of each joint is getting sent to the shared autonomy and the intent recognition. And then the inference probabilities will be sent to the shared autonomy, and the overall output is going to be the command sent to the robotic arm. Is there any questions on this so far? Why is the slide empty? No, not empty, sorry. Okay, this is just a little snippet of a video that kind of shows. So this is an end user. He has this arm to use every day in his house. And right now it's mapped into a 3 degree of freedom joystick that he uses also to operate his wheelchair. So he's trying to pick the banana up off the floor. In this video, it doesn't show the arm even moving to the banana. He's just trying to pick it up. So you can see that it's rather a long process, so time consuming and cognitively tasking, which I'm going to talk about on the next slide. Also, it's interesting to note that when he's operating the arm, you can't move the wheelchair at the same time. So that's also a different problem that I find rather interesting. How can we do these things at the same time? But that's a different topic. Okay. Next slide. Okay, here we go. So different control interfaces. In this work, they considered 2 different control interfaces, the 3-axis joystick, which is commonly used, and a sip and puff system where it has 1 degree of freedom. So the authors were interested in answering kind of the question, how does the control interface used affect the intent inference performance? So they use a Miko robotic arm. This is from a Canadian company, Canova, based out of Montreal. It has 6 degrees of freedom and it has a 2-finger gripper. So this question is quite important in the domain of assistive robotics because if you have severe motor impairments, then you have really limited control interfaces in order to operate the robot. So we really want this shared autonomy to kind of take some of that cognitive load off of the user. And we were interested in increasing or decreasing the time it takes to complete tasks. And one other thing is you've noticed, so here with the 3-axis joystick, we have 3 different modes. We have the translational mode in Cartesian space, the wrist mode, which is just angular, so then you could point it in the direction you want, and then the finger mode where you open and close the gripper. So we have 3 different modes for our joystick. This increases to 7 for the sip and puff because it's a 1 degree of freedom system. So we have forward, backward, left, right, up, down, etc. So the dimensionality of the control signal that is being sent is far lower than the control space of the robotic arm. So the way that we get around this is that because we can't control all 6 degrees of freedom at the same time, we do this thing called mode switching. So if you notice in the previous window, or in the previous video, it kind of shifted where he was almost looking at the banana and then kind of shifted to the right and then went back and then back. So he's actually hitting a button with his elbow that's inside the arm of his wheelchair in order to switch between different modes to get the arm to move where he wants it to. So the 3-axis joystick teleoperation requires at minimum 3 control and then 6 for the sip and puff.
Can you explain what exactly is sip and puff? Like, why is it called that? What is it?
It's just like puffing air, essentially. You put it in your mouth. Yeah.
Okay, thanks.
It's like a binary signal on and off.
Are there many times you can use a sip and puff but can't use gaze recognition? And there's probably some.
mean, gaze would be more of like an implicit observation that you could use, and it's highly reliant on like the calibration and the underlying equipment and hardware. Whereas like the sip and puff, I think it's quite reliable and commonly used.
Okay.
Yeah.
Yeah, we used gaze control for a wheelchair targeting ALS patients a few years ago, and sip and puff is going to be much more reliable than gaze.
Yes.
Oh, also, while I'm talking, have you mentioned yet what kind of intents you're talking about? Because if you're just trying to figure out, does the person want to pick up the banana or pick up the doll, then you could just show them two choices and say, which one do you want? So it's got to be more general than that, but it can't be the user wants the robot arm to dance, or, right? There's got to be some constraints.
Yes, we're going to mathematically define what the goals are for the intent problem here right away. I wish we could make them dance though, that'd be great. Okay. So this boils down to the intent inference problem. So we're interested in how can we simplify it. So previous attempts to simplify this problem is either focused on inferring what their intent. So let's just assume that the intent of the user is like a positional goal of the cup that you want to go pick up. But there could be multiple cups on the surface. So which one do you want to pick up? Oh, I'm sorry, I'm looking at Discord. Lower degrees of freedom, necessary or 6 degrees. A lot of time in assistive robotics, we use the 6 degrees or 7 degrees of freedom because it's almost trying to like anthropomorphically mimic a human arm. Because we want the devices to be as less obtrusive as possible and very like to create movements that are similar to our own. So we don't want the action of the arm to surprise anybody around it, right?
So I guess the question then boils down to, is that good, right? If you have too many degrees of freedom and we get people confused about mode switching, which I understand, because if I think about my arm, I don't think about 6 degrees of freedom. I think about grab the banana, right? And that's all automatic. But if you've ever driven any of these industrial machines or seen them work, the things that people can do with them are really quite cool. And like in a comparable way to a hook hand being a reasonable prosthesis, maybe 1 or 2 degrees of freedom gives you better results than 6 if we're just confusing people. I guess that's where my head's at.
Well, if you only have 1 or 2 degrees of freedom, you'd only be able to make movement in the one plane. So then how would you carry out tasks in 3D space?
Sure, maybe 3 then, but less than 6. I
guess. A lot of times having like an overdetermined system, if we have more degrees of freedom, we can solve, so there'd be multiple ways of solving the same task. So say that, so like the end effector is the gripper of the robot, right? So if you define its goal position as XYZ alpha beta gamma somewhere in Cartesian space, that's the position that you want your end effector to go to. So then if you have 6 degrees of freedom, so you have more joints, then you could reach that at goal position with multiple different configurations of the previous joint. So you could have like, my hand doesn't move, but my elbow's up here, or maybe my hand's kind of moving, but I can't stop my hand from moving. So you have different configurations to reach the same point, which can be very helpful, especially if we want to constrain trajectories to say not like bust through the person's body or any other kind of obstacle avoidance, or if you want to constrain it to the realm of human-like trajectories, then it becomes helpful to have those extra degree of freedoms to kind of give you more to play with. Does that make sense?
Yeah, thank you.
Okay, welcome. Where was I? So, I can't remember what it was, but one approach that's been used previously is to infer the user intent by having them either communicate what the goal is explicitly. So clearly state, that is the cup I want. Here's its position. Go get it for me. Okay. You could use like touchscreen interfaces, but this could potentially lead to like weird collaboration or an increased cognitive load on the user, which is what we're kind of aiming to decrease in the first place. So then a bunch of work has been done on how to investigate the use of nonverbal communications like eye gaze and gestures, because it's been shown that like gaze patterns can be used to perform the anticipatory actions. So your eye gaze actually is going to go towards the object before you start reaching for it. So that's been used. And then within the context of shared autonomy, the intent inference, it's often represented as a confidence in the prediction of the intended goal. So say that you have a bunch of objects in the scene and you don't know which one we want to pick up. So we can represent it as the confidence based on instantaneous observations. So in this work, the authors consider a probabilistic modeling of implicit observations and then compute the belief over the space of possible goals within a Bayesian filtering framework. So their approach incorporates both a distance-based likelihood observation, so like the distance from that goal, and then they fuse in also the control interface of the user. I'm gonna take too much time. Okay, Michael, I think that this is where you're taking over.
Thanks, Laura. Yeah, so to kind of formalize what we're talking about and how to do that mathematically, these are the more technical details of the paper, although that is not really the focus. So I'll try to kind of go through this fast enough to give you a high level understanding so we get to the more interesting part of the experiments. So how do we actually formulate this mathematically? So the intended goals, and so kind of the problem setup is the intended goal is unknown to the robot, and this goal can be changed dynamically. So maybe a person wanted the banana in the first place, but now they want to pick up the apple or something, some other fruit. And so the robot must infer the most likely G star of a set of G, where G is our goal tasks or whatever the user is trying to reach. So we have a discrete predefined set of accessible goals, which I have the picture on the slide to the right there to kind of give you an example of that. Although from my end, the text isn't very clear, but those are like 3 different tasks of, I think, pouring, grasping, and something else from a different paper, I should just note. And so, yeah, and then this G star can change during the process, right? And so they model this as a posterior of some given feature set, which is in the domain of real numbers of k by t, and this goal. So k is the feature dimensions, which might be the robot state, the action, or whatever other information you might observe from the person. So like implicit feedback, eye gaze has been mentioned, or things like that. And then t is just for the time step, because this is a like sequential decision-making process. And so we're going to have features over time to kind of make our decisions on what is the posterior distribution of whatever goal the user is interested in. And so the model that we are interested in is this equation at the bottom of the slide, where we have this bt of g, which is proportional to the probability of our feature t given a goal. And the next term is the marginalization over all possible goals in the previous time step. And so that equation is kind of the crux of their algorithm. And so Laura, if you can go to the next slide. So this is kind of the core algorithm that they talk about that they use in their paper, where we're given some goals to start with, some initial prior distribution over how likely we think any goal is at the beginning of our control. We initialize our posterior distribution as we get more information from the user and whatever goal we think is most likely currently, and some sort of normalization constant because we need to have a valid probability distribution. And then after we have done our initialization, while we're executing whatever the task of interest is, we're going to update our beliefs about different goals given the information that we are collecting. So Laura, if you could go to the next slide. So the key kind of equation is this thing in the for each statement, G in the domain of all possible discrete goals, where we first have our feature probabilities given a particular goal, which we assume is independent. So every single feature we assume has no impact or influence on other features that we can care about. And so that's just the product of each feature given independently. So on the next slide. So then we have this term that is our marginalization of all previous information from the previous step. There are some assumptions that I'm glossing over. So if you're confused on where this comes from, just take what I'm saying as it is, and I apologize. But again, I'm trying to blow through this because this is not that interesting in the context of the paper. So we're going to marginalize out all previous goals. Next slide. And so this first term is kind of our belief of the goal at the current time step, given the goal at the previous time step, to kind of relate the transition between goals. Again, kind of the banana thing. So maybe we're reaching for the banana that's over here, and all of a sudden it's like, well, I actually want to eat the fruit. And so the goal, the transition between those two things. And then one more slide transition. And so a key thing that they mentioned in the paper is that we can actually define this as a recursive relationship and kind of not keep like a huge memory of all previous information up to that point. We just need to know the calculation of this BT-1 probability distribution that we defined on the previous step. And so then like we wouldn't have to unroll all of our history. We just need that recursive term to do our calculations of the posterior distribution. And so I don't think there's another slide for me highlighting boxes, but then after we've updated the thing, yeah, so we have our probabilities, we've picked whatever goal we think is the most likely. So how do we actually use these things to kind of adapt the actions or whatever to help a person in the autonomous system? So first, because we are a Bayesian framework, we need some sort of uncertainty, which we'll use. And the way the authors define it, although they don't really expand on it in this paper, is we're going to define this confidence, where probability G star given our features is going to be, you know, our most likely goal subtracted from the second most likely goal, which is going to kind of give us the gap of like how probable the most likely thing is compared to the second most likely. You could probably play around with that, but that's just how they define it in the paper. And so given that information, we're going to have this blending of some actions, which for the sake of presentation is just this black box of how we determine these things. Are there any questions in? Yeah, okay, we're okay then. All right, and so we're going to blend these actions of the robot doing something with what the human desires by this linear interpolation between the two actions. And you'll see that there is this parameter alpha. And so you might be wondering, where does this alpha come from, besides being confused on where the actions come from? So the authors defined this very simple function of how to select your alpha, where we're going to predefine user specified or whatever, 3 threshold quantities, where the lower bound is going to be 30%, the highest is going to be 70%, and then delta is whatever that is in between. And so our confidence metric is the middle thing in this last equation from the first bullet point. And so these deltas are, and this is how we determine how much to weigh, you know, human information with the robot's information to determine the action to use for the robot. Yeah. And that's kind of a brief overview of the method, but one thing I should mention is that if I recall correctly, they do mention that this paper is kind of building on previous work where they specify more information about the framework as a whole. And there are a lot of details that I'm kind of glossing over. So going to pass it back to Laura to talk about the more interesting bits of the human interaction. Oh, and if there's questions, you know, feel free to ask, but don't want to stop you, yeah, from discussion. But
yeah, so essentially here they're kind of interested in, as they get more confident in what their prediction is of the intended goal, then they're going to give more control to the autonomous system as opposed to the human. So in this work, they actually carried out some really nice experiments. Not actually, but they did. So they implemented 2 different observation schemes that they were interested in testing. So the first one, within their framework, just implemented a single modality, which was the proximity to goal, so the Euclidean distance between the end effector and the goal location. And then the second one, they used both this proximity metric and then also the user control input signals. So they did this to show that they are able to fuse multiple observations within their framework and with increased improvement. So we could take this framework and see if we could add in, say, eye gaze or any other sort of implicit observations, facial reactions, and see how that improves the control methods. They also compare this with 2 prior methods that have been tested and published. So there's the I I could be pronouncing that wrong, based inference. So in this one, they associate a confidence in the prediction as a simple hinge loss function, where it is assumed that the closer the goal is, it is more likely that that is the intended goal. So the thing about this one is that it's only based on instantaneous observations. They use the Euclidean distance, but it doesn't take into account any of the prior trajectories. So the memory-based inference, this one utilizes information about past trajectory history in order to predict the likely goal. So you could almost make a prediction on which one might perform better. Matt, I just noticed it's 12:20.
So how many slides do you have left?
I'm on slide 16 of 24, just on the experiments and then some of their results. I could try to fly.
Well, how about this? People who need to go are absolutely welcome if they need to be somewhere else. But for those of us who, and I also, if you've got another 5 or 10 minutes, if you're able to stick around, then let's give Laura the extra time so that she can wrap.
And if you do have to go, I'll put the slides in Discord. If you have any questions about them, you can reach out and ask me.
Oh, sorry. Let me interrupt then, because one thing I wanted to say that remind people at the end of the class. Remember, as you're working on your final projects, I'm always happy to meet. Just ping me. Hopefully, the comments that people are dropping will be useful to the presenters, but also, if you have not presented yet, it's probably worthwhile for you to go through those, because you might get some hints and tricks. Like, it's kind of nice if you can mention why a paper is relevant to you. All right. With that, I'll stop talking and let Laura take it over again.
Thanks, Matt. So in their experiments, they evaluated these 4 different inference techniques against 4 different performance metrics, which I really appreciated, because a lot of the time we see just like one performance metric evaluated, but here they covered the percentage of correct positions, the cross entropy loss or log loss, task completion time, and number of control mode switches. So the last 2, those are highly relevant to assistive robots, because that has a direct impact on kind of whether a user is likely to keep the system and use it, sort of like going back to the prosthetics. Like, why would you switch back to your hook, right? If it's too complicated to use or takes too much time, there's too many mode switches. Yeah, so I'll just pop through this because you guys probably know what this stuff is. So they completed 2 different studies. One, a human inference study, where the aim was to kind of ground the complexity of the intent inference problem by studying how humans, the ability of a human to inference what the goal is of the motion of a robotic arm. So they did this under 2 different motions evaluated. So one where there was no change of intent. So the robotic motion maintains a single goal from start to end. And then the second is the change of intent. So the robot starts moving towards one goal and then changes direction and moves to a second goal. They did kind of a 5-minute training period where the subject watched the video to see like, oh, okay, the robot's reaching for something. And then they had pre-recorded trajectory motions that fell under one of those 2 categories. And the human subjects were tasked to observe the motion of the robot and to predict what object was the intended goal just by verbally mentioning it. And then they would write it down or click a button, I think. So they mentioned the object name or number, and while doing so, they were allowed to change their inference at any time during the robot motion before it got to its goal location. And they were also given the option of expressing uncertainty about the intended goal. So they could say like, not sure what it's reaching for. So this is the results, or one graph from the results of this study, which is quite interesting. So it's shows their inference performance on the demonstration trajectories. Sorry, my dogs. So it's interesting to note that in general, humans when compared with the autonomous. Sorry, my one dog is deaf, so I can't just yell at him to stop barking. So they tend to make fewer incorrect predictions, but they also indicate more uncertainty in those predictions. This really has implications within the assistive robotics domain, since quite often, if you are providing the wrong assistance, it could be worse than providing no assistance at all. So this uncertainty metric we're really interested in knowing. So they also found that the human subjects were able to quickly switch their predictions. In the case of the change of intent, they were able to catch on, but they did have comparatively more incorrect predictions than the autonomous system. It's really interesting how the uncertain bars, they don't really change between the change of intent and no change of intent. So in either case, if you're uncertain about the subject or the goal location, it didn't really change. Sorry, that didn't make too much sense. So the second study that they carried out was an autonomy inference study. And the aim of this was to evaluate how well the autonomy is able to infer the intent of the user under teleoperation, and how that inferred intent affects assistance in shared autonomy. So this is where they're going to evaluate the joystick versus the sip and puff interfaces. So they evaluated on the 4, so remember the amnesic, memory-based, and then the 2 that they did for this study. So they recruited 24 different participants, 24 participants without motor impairments, and then 4 end users, and did the teleoperation without assistance, and then shared autonomy with assistance. So, okay, we'll just move forward. These are the 4 tasks that they set out to during this experiment. So the first 3 tasks were involved object retrieval. So reach and grab the object. The goals are the approach grasping pose. So that's X, Y, Z, alpha, beta, gamma. So the final pose of the end effector around the intended object. And the 4th task was more complex. It was a manipulation task. So the goal in the manipulation task was the pose of the initiation of the pour over bowls and then placing it in the dish rack. Next. Is this clear? I'm looking at it now and it doesn't look clear at all. Okay. I'll just talk about it, and I guess if you're interested, you can look at the paper. The more thick lines is the change of intent, and the dashed lines is no change of intent. So in general, you can see that the no change of intent performed comparatively better to the change of intent. The left 2 graphs is the 3-axis joystick. The right 2 is the sip and puff. The top 2 is subjects without motor impairment, and the bottom 2 is the end user group. So it kind of general overall, the amnesic inference performed poorly and failed to get the prediction correct for a higher percentage of time as compared with the other methods. Comparatively, their inference method that incorporated both the distance metric as well as the human input signals from their control interface, that performs better, especially in the change of intent trajectory. So the memory-based approach, which utilizes the information from the past trajectory history, had a really hard time when there was a change of intent, because this history actually caused a hindrance in the control. Yeah, maybe because you can't see the graphic, I'm not going to speak more to it. Is this one a little more clear? Oh, okay. You can just look at the columns. So the blue is memory-based. Orange is their first inference method that just takes the distance, and the turquoise is their second one that incorporates both. The statistically significant trends were that the green bar, it significantly outperformed all the memory-based approaches for nearly all change of intent scenarios. So you're looking, this is the average log loss on the y-axis, so the lower the better. Interestingly, in the no change of intent trajectories, the memory-based did perform quite well, better in most cases. So really this kind of emphasizes that although the memory-based methods for intent recognition, they perform very well, but in unstructured settings in the real world, we change our mind a lot on what we want to do. Like I can find myself walking to go get water and then I end up getting cereal or something. So in real life, it's more realistic if we were to use an inference system that is able to accommodate for this. So this one, just overall on the left-hand side, this is the task completion time. So we can see that compared with just base teleoperation, which is the red bar, both of their methods perform better. Also, you can note, so the 3-axis joystick and then the sip and puff, it looks like they're the same, but they changed the range of the y-axis. So you can't see it, but the sip and puff actually takes substantially longer time than the 3-axis joystick, which makes sense because we have far more modes to switch through. So overall, for both interfaces and subject groups, you get better and faster inference during shared autonomy operation with their second method, and especially when compared with the direct teleoperation. So this kind of highlights the overall benefits of shared autonomy in assistive robotics, and not only reducing the task completion time, which is the left 4 graphs, but the number of mode switches, which is on the right, where you could see that they were actually drastically improved. And just the main conclusions. So the main key takeaway of this paper is that inferring the intended goal of a robot is a challenging task, even for humans. You see, remember, they were very uncertain a lot of the time. So humans tend to make fewer incorrect predictions, but are more uncertain. And their results show that this is a viable method for kind of inferring what intended goals are. And it's, well, at least I think it's interesting.
So if let's say you're using a sip and puff and you drive your wheelchair up to a table with 3 objects on it, why can't the system just ask you, do you want the left one? No puff. Do you want the middle one? No puff. Oh, then it must be the right one.
It could definitely do that.
Okay.
I think one reason is that it's, at least is my limited understanding of autonomy, is that people like to feel they're in control. So I guess one reason it wouldn't be favored by a user is that they want to feel like they're the ones picking up the object, I guess is the thinking. But I'm fairly new when it comes to robotics, but that's what I've heard in like previous presentations and stuff we've had in our lab. So yes, you could just ask them and be like a servant master kind of relation, but I don't think that's what people would prefer.
Yeah, so Michael, you're both correct. So like a large portion of my research is like where along the kind of scale of from full autonomy to full teleoperation, where do you want to be? And there's been studies that have shown that like as the level of disability increases, that they actually prefer to have more control over their assistive devices. But then also if you're having a bad day, say, then maybe you want the option of a more autonomous system. So like previous work done in our lab has basically, instead of verbally asking what you wanted, it's automatically segmented the objects in the scene, and just on a touchscreen interface, you just click on which one you want, and then the robot would go and pick it up for you. So it's not so much about having one thing to do everything, but have different options to present to the user based on the level of control that they want on any given day.
Very cool. Thank you. Any other questions?
I have a sort of obnoxious question that doesn't really have much to do with the paper, but I'm still stuck on this. I find this assistive robotics thing pretty cool, but I'm trying to rationalize, like, so when we test on people, we end up usually testing on somebody who has a disability, correct?
I mean, you should try and incorporate both able-bodied, both sort of how they did in this study, but it's not always possible. There's a lot of ethical and hoops to jump through.
Yeah. So I mean, they use a 3-axis joystick, but they have 6 degrees of freedom. So why not 2?
Why not 2 what?
2 joysticks.
So depends on, I guess, the level of disability of the individual. A lot of the times, even though they have a 3-axis joystick, maybe you have a lot of tremors, and it's difficult enough for you to control that joystick, let alone adding in the additional complexity of another one.
Yeah, so I guess my question is poorly phrased. What I'm curious about is, if you have a normally abled person and 2 3-axis joysticks, can you effectively control a 6 degrees of freedom arm?
Yes, you could. I actually have this lovely thing called a space mouse.
Okay.
So it has full 6 degrees of freedom. So we have the translation and the angular. And I have it mapped up to the robotic arm, and it works. It definitely works, but it is still challenging to use. And there's that learning curve. And sometimes it just does weird things, because if you're applying constant velocity in, like, say, positive X, in different configurations of the joints, it's gonna, like, applying a constant force in the X direction, it's gonna move at a different velocity. So it's, yes, the answer to your question is yes, it is possible.
Cool, thanks.
All right, well, we should probably wrap here since we're over time. But thanks, Laura, Michael. That was really cool. Now I'm really looking forward to seeing your final project. Please, and feel free to continue this discussion on Discord. If you can drop your papers and slides in there, that'll be awesome. And otherwise, I will see you on Thursday. So thanks, everyone.
Thanks, everyone. If anybody wants to chat more about it, just let me know.